and often two or more. For the second topic of this unit, we will be talking about the classification and chemistry of carbohydrates. This can be easily or essentially classified according to the number of sugar units they have. So we have here the four major classes of carbohydrates. We have the monosaccharides, disaccharides, the oligosaccharides, and the polysaccharides. Monosaccharides are also called simple sugars. Let me just get the pen. Okay, so monosaccharides are also called simple sugars. They are also called the single polyhydroxylated aldehyde or ketone unit. Disaccharides, on the other hand, consist of two monosaccharides linked together by glycosidic bond. Oligosaccharides are made up of 3 to 10 monosaccharide units, while polysaccharides are long chains of monosaccharide units. We first discuss monosaccharides. So monosaccharides have the general formula of CH2ON, like what we've discussed a while ago. So the simplest monosaccharide would be those that have 3 carbon units. So we have here the glyceraldehyde, which is an aldotriose, and a dihydroxyacetone, which is a ketotriose. So we will discuss in the next slide what is the difference between aldose and ketos. We are now here to classify monosaccharides. So first is based on the carbonyl group present. Okay, so we have two classifications for this. We have the aldose and ketos. So when we say aldose, these are monosaccharides wherein the carbonyl group is at the end of the carbon chain. So again, when we say aldose, the carbonyl group is at the end of the carbon chain. That is in an aldehyde group, then monosaccharide is called an aldose. On the other hand, ketos are monosaccharides wherein the carbonyl group is at another position in a ketone group. So that is the difference between aldose and ketos. So the next one is the classification of monosaccharides based on the number of carbon atoms. So we have here 5. So the first one is triose. So we have here the keyword, which is the prefix tri, which means 3. And we have tetrose, which has a prefix of tetra, which is 4. And pentose, which is 5, hexose, which is 6, and heptose, which has 7 carbon atoms. So now, let's try to classify monosaccharides based on, again, the classifications we have discussed a while ago, which is based on the carbonyl group present and based on the number of carbon atoms. Alright, so let's try the first one, which is a glyceraldehyde. So we have here, so based on the carbonyl group, we have here, you can see that it is located at the end of the carbon atom or carbon unit. So it will be called aldo. Okay, and why does it be called triose? Because it has 1, 2, and 3 carbon units. So that would be, so glyceraldehyde will be an aldotriose. On the other hand, we have dihydroxyacetone. So we can see here that the carbonyl group is in another position other than the end of the carbon unit. So we will call this a keto. or ketose. So we will now count the number of carbon. So we have here 1, 2, 3. So the final answer would be a ketotriose. All right. The next one is the D-glucose, which is, and again, this is, or the carbonyl group is at the end of the carbon unit. So if we count the number of carbon atoms, we have 1, 2, 3, 4, 5, and 6. So we have here an aldohexose. D-fructose, on the other hand, wherein here you can see that the carbonyl group is in the middle, so we will call it a ketose, and it has how many carbons? We have 1, 2, 3, 4, 5, 6. So we will call it a ketohexose. The same applies with here. In here, so we have the D-ribose, which is an aldose because it is in the end of the carbon unit, and also it has a 1, 2, 3, 4, 5 carbon atoms. So we will call it a or an aldopentose. And the last example is the 2-deoxy-D-ribose. So we have here an aldose again, and we have 1, 2, 3, 4, 5, which is also an aldopentose. Monosaccharides usually contain many chiral carbons and thus exist in a number of stereochemical forms that can be described as Fischer projections on paper. In general, 2 raised to n stereoisomers can be found in a molecule with n chiral centers. As you can see here in the figure, that there is, you can see a stereochemistry in all monosaccharides. So it says here that all monosaccharides except dihydroxyacetone are optically active. So you can see here that there is a mirror image, or there exists a stereochemistry for monosaccharides. We have 2 configurations. So we have here the D and L configurations. So we have D and L. So when we say that it is in the D configuration, this is when a hydroxyl group is at the right side of the penultimate carbon. So here is an example of it. So we can see here that the hydroxyl group is at the right side of the penultimate carbon. So we will call it a D-glyceraldehyde. On the other hand, when an OH group is at the left of the penultimate carbon, we will call it an L-glyceraldehyde. So that is the difference between the configurations of D and L. Alright, so how do we compute for the number of stereoisomers for a monosaccharide? So we have here the formula 2 raised to n, wherein n is the number of chiral centers. Okay, so when you say chiral centers, here are some of the examples. So we have here the D-erythrose. So we have here 2 chiral centers. Okay, but for aldotriose, so meaning there are 3 carbon units in a carbon chain. So since there is only 1 chiral center in that monosaccharide, you will only get 2 stereoisomers for that. So an example is the D-glyceraldehyde and L-glyceraldehyde, which is given a while ago. So here you can see that there are 3 carbon units, but it has only 1 chiral center. So same applies here in the L-glyceraldehyde. So it has 3 carbon units in a chain, but only 1 chiral center. So if you compute that, you will only get 2 raised to 1, which you will get 2 stereoisomers. On the other hand, if you have an aldotetrose, so since you have 4 carbon atoms in there, so 1, 2, 3, 4, you will get 2 chiral centers for that. Okay, so if you compute that, 2 raised to 2, you will get 4 stereoisomers. So same applies with the D-threos, which has 4 carbon units, but only 2 chiral centers. So then 2 raised to 2 is equal to 4 stereoisomers. Alright, so how about for those monosaccharides that has 5? So we have here an aldopentose, so meaning they have 5 carbon units. Okay, so we have here 1, 2, 3, 4, and 5. So meaning you only have 3 chiral centers. So that is for D-ribose. So if you compute that, so since 2 raised to n, so we will have 2 raised to 3, you will get 8 stereoisomers. So same applies with the other aldopentoses like D-arabinose, xylose, and lysose. So we have here 1, 2, 3, 4, 5 carbon atoms, but only has 3 chiral centers, meaning same applies with the formula, wherein you will just input 3 in here. So 2 raised to 3 gives you 8 stereoisomers. Are here in the aldohexose, but first let me just get the pen here. Alright, so okay. So we are given an aldohexose, actually too many aldohexoses here. So when you say hexose, meaning you are given 6 carbon units in a carbon chain. So we have here 1, 2, 3, 4, 5, and 6. So how many chiral center does it has? Okay, so we have here 1, 2, 3, and 4. Okay, so if you apply that here in the formula, so 2 raised to n is equals to 2 raised to 4, which will give you 16 stereoisomers. So same applies with the other aldohexoses here, like D-altroses, D-glucose, D-mannose, glucose, addose, galactose, and tallose. So again, they all have 4 chiral centers, so they will give you 16 stereoisomers. Okay, so actually you can see here that these are stereoisomers of each other. Okay, so they will just have a change or in the mirror image, and their hydroxyl groups are positioned in the different parts, or they can be in the left or right. So it will give you different monosaccharides. So now we go to the definition of epimers. So epimers are sugars that differ in configuration in only one carbon other than the penultimate carbon. So you can see here some examples. So we have here the D-mannose, okay, the D-mannose, D-glucose, and D-galactose. As you can see here, that there are differences on the or in the configuration of the carbon, of only one carbon other than the penultimate carbon. As you can see here, mannose and D-glucose are epimers, okay? So there is a difference in the configuration on the second carbon or the first chiral center, as you can see here. Okay, So you can see here that in the D-mannose, the hydroxyl group is in the left, while on the D-glucose, the hydroxyl group is on the right of the penultimate carbon, which is the carbon number 2. On the other hand, glucose and galactose are epimers also, but you can see here that there is a difference between the configuration of carbon 4. You can see here that in the glucose, hydroxyl group is in the right of the penultimate carbon, while in the galactose, you can see that it is in the left of the carbon 4. So these are examples of epimers. In here, these are epimers of aldohexoses. So when you say aldohexoses again, you have 6 carbons, okay? Like the D-allose. Actually, all of these are epimers of glucose. You can see here that there are different configurations on the penultimate carbon. Like for example, mannose, there's a difference in here with glucose. So here are some of the examples of the epimers of aldohexoses. So in order to describe both the functional group as well as the number of carbons, we give detailed generic names to monosaccharides. To illustrate, for a monosaccharide which is composed of an aldehyde with 6 carbons, we refer it as aldohexoses. Meanwhile, when its functional group is a ketone, we call it ketohexose. Sometimes, ketone-bearing monosaccharides are simply named by inserting ul or ul with the generic names. So as you can see here, let me just get the pen here. Okay, so to give it a generic name, you just have to insert ul here. So from erythrose to erythrulose, and for ribose, you have just inserted here ribulose or ul to become ribulose. In aqueous solution, simple carbohydrates exist in cyclic forms. Monosaccharides typically form internal hemiacetals or hemiketals, as you can see here. And hemiketal, in which the aldehyde or ketone group joins a hydroxyl group of the same molecule, forming a cyclic structure. This can be represented as the Howard perspective formula in here. The formation cyclic monosaccharides render an asymmetric carbon or anomeric carbon and 2 stereoisomers known as alpha and beta forms. The alpha and beta forms. Isomeric forms of monosaccharides that differ only about the hemiacetal or hemiketal carbon atom in their configuration are called anomers. The anomeric carbon is called the hemiacetal or carbonyl carbon atom. So which hydroxyl containing carbon reacts with the functional group of this simple sugar? That's right. C5 of D-glucose reacts with carbon numbers 1 and 2 of respectively of each molecule. So in an aqueous solution, the alpha and beta anomers, you can see here, interconvert through a process called mutarotation. The classification alpha reveals that the hydroxyl group at the anomeric center is on the same side as the hydroxyl group of the farthest chiral center in a Fischer projection, while beta means that these hydroxyl groups are on the opposite side. So we have here an example, which is the alpha D glucopyranose. So this, why is it called alpha? I said a while ago. It's because the hydroxyl group of the anomeric carbon or anomeric center is on the same side as the hydroxyl group of the farthest chiral center. On the other hand, this is called beta D glucopyranose because the hydroxyl group in the anomeric center is on the opposite side of the farthest group or the farthest chiral center in the carbon chain. So same applies with the D-fructose. So here, okay, so you can see here that it produces an alpha D fructofuranose and beta D fructofuranose. Okay, so if it is already a 5-carbon sugar, so here it will become furanose, and like the other one, it is pyranose. So we have here the fructofuranose.